This is on probability. Y'all have not had a lot of probability since 6th grade, so we'll talk a little bit about it in general. Probability, you're probably used to things like putting marbles in bags and choosing them out. That's an exercise in counting various things. Counting has a lot to do with probability. What is probability? It's the measure of the likelihood that an event will occur. We talk about that as a ratio, and the ratio will be between 0 and 1, with 0 being an impossibility and 1 being a surety. Something that is only in theoretical probability, not in experimental probability or real life. In real life, there is nothing that's impossible, empirically anyway, and there is nothing that's an absolute sure thing. So if I say, I'm going to take this pen and drop it, will it hit the paper? I put it here, I drop it, does it hit the paper? What's the probability of that? Well, one might think, in theory, given my limited scope in my mind, that yes, you could say that it is a sure thing, that when I drop it under these circumstances, it will hit here. So that would, in theory, be a sure thing, so that would be a probability of 1. Or if, but it's not necessarily true. For example, but I'm going here to drop it. It might be that, I don't know, hawk flies in through the window. But as I drop it, and before it hits the paper, the hawk grabs it and flies off with it. Or more possibly, a student sitting here. As I'm going to drop it, says, hey, that's a nice looking pen. I think I'll take that pen. And as I go to drop it, swoops her hand in and takes the pen so it doesn't hit the table. So, is it really a sure thing? No, it's not really a sure thing. Or another thing, perhaps there will be a local discontinuity in gravity. The gravitational constant of the universe will change right here. And instead of falling down, it'll fly off and not hit the table. Well, anyway, lots of extraordinarily improbable things could happen. So we'll say that in real life or in experimental probability, there's no such thing as a sure thing or as an impossibility. The ratio that we have for probability is the ratio of the number of favorable events, that means what we're looking for, what we want to get, over the total number of events in our story, in our circumstance. So the number of favorable events, the ratio of favorable events to total events in the numbers. Or a short way to think about it is what we want to what we have, the ratio of what we want to what we have. This really doesn't work that well for geometry. What you're accustomed to is counting things. How many outfits can you wear with a pin oak dress code of a blue shirt or a white shirt or a gray shirt, and blue pants or khaki pants or skirt, and how many combinations would there be? You count them, that would be the total number, and then you count the outfit that you want and you make a ratio that way. Or you put 10 marbles in a bag and 7 marbles are red. What's the probability of drawing out a red one? That would be the favorable event would be red. The total number of events would be, in this case, 10. So the probability of drawing a red would be 7 out of 10. Okay, well, I said that doesn't work all that well for geometry. Let's explore why it doesn't work all that well for geometry. So we've got a line segment here. The line segment will be A, B, C. So let's say this is 5 units and this is 4 units. What's the probability that if I choose a point on line segment AC, that it's also on line segment AB? Well, you're probably going to say pretty quickly that it is 5 out of 9. And that's correct. You're saying, well, what's the big deal? I thought you said we couldn't really do it. Well, we really can't. When we're talking about the way that we've done it before, we're going to count the things. Count for me, will you, all of the points between A and B on this line segment. You say, that's kind of interesting. That's an infinite number of points. Okay, well, if you put the numerator as the infinite number of points, well, then tell me how many points are there between A and C contained on line segment AC. Well, that's infinite too. So then are we going to say the ratio of infinity to infinity and somehow reduce it to 1? No, we're not going to do that. No. Boggles your brain. No, Okay. So we really won't work this counting thing that we're accustomed to. So what we'll do is a measurement, and we'll make a ratio of the measurements. So in this case, the measurement of the line segment AB is 5. The measurement of AC is 9. So the ratio that we're looking for in geometric probability is 5 to 9. So the probability of choosing a point on segment AB from segment AC is 5 out of 9. A little review of terminology. We'll call this the probability, big P. This is not multiply. Probability of landing on segment AB is 5 out of 9. So the probability of the event occurring of landing on or choosing a point from AB is 5 out of 9. We do it by measurement. We don't do it by counting. We use the length. So what about, let's do an aerial one. I've got a board. Here's my board. Dimensions of my board are 10 units by 7 units. On my board is a circle painted. Its radius is 2. I'm going to throw a dart at the board. The dart will hit the board. What's the probability that when it hits the board, it hits within the circle? Now we're going to need the area. We're going to need the area of the circle, and we're going to need the area of the rectangle. And we'll make a ratio. So the area of the circle is pi r squared, where r is 2, or 4 pi. Approximately 13, we'll say, just for the purpose of this simplistic argument. So what's the area of the rectangle? 10 by 7, or 70 square units. Therefore, the probability of choosing a point on the circle, or the dart hitting a point in the circle from the board, is the favorable over the total, what I want over what I have. 13 out of 70. Another example here. We have an archery target. We have that the area, the diameter. We have the diameter of the bullseye, I'll put B for bullseye, is 16. The diameter of the target, T for target, is 80. The question is, what's the probability that if you hit the target, you will hit the bullseye? You need to find the area of each reason. Now, a caution here. When you're working on something like this, please at least write down what you're doing before you start pushing calculator buttons. The reason for that is when you're working with irrationals such as pi or many of the square roots, very often, more than one would think, they'll cancel or simplify in such a way to give you a much more accurate answer than you would if you'd have just punched it into the calculator. So let's go ahead and do this. What we're going to need is the ratio of the area of the bullseye, what we want, to the area of the target, which is the whole thing that we have. The area of the bullseye is going to be pi times the radius of the bullseye squared. The area of the target will be pi times the radius of the target squared. Oh, look, how convenient. The pi's cancel. So we're left with, now this is radius, we've got diameter. So what we're left with here is the radius 8 squared over the radius of the target 40 squared, which is 16 over 1600, which is 1 to 25. So we have an exact number for the probability of hitting the bullseye. A few more things here. Sometimes you're going to be asked to do an irregular area, and depending upon the degree of accuracy that's needed in your calculation, sometimes you can use a grid to estimate. This is kind of a little bit of the type of thing that you'll be doing in some higher level math courses. What we're going to do is estimate. Like, for example, look right here. Okay, I'm sorry, your dog dropped a ball in the park. The scale of the drawing of the park is shown. If the ball is equally likely to be anywhere in the park, estimate the probability that it's in the field. So what we have here then is an estimation technique. If you look up here, generally speaking, all of this curve is about half of the rectangle in which it's enclosed. 1, 2, 3, 4, 5, 6, 7. It's about half of 7, or 3.5. This right here, that's about half of 2, or 1, and that's a little bit less. So you can estimate how many here are by counting the squares. Then you'll take the area of the field as the numerator and the entire estimated area as the denominator, and that will give you your probability of finding the ball in the area that's easier to search for the ball. A few things to notice here. First off, do some of these problems. The probability on a segment, notice that, how that can work out. What's it going to be? And here are a few more problems that you might wish to work on. And here endeth the lesson.